Hello, everybody. Today we'll be talking about countability and separation axioms and their role in point set topology. So we're going to start out by going through what is the relevance of these axioms or additional constraints that you can put on a topological space within topology more generally. And then we'll talk about two broad sets of axioms, the countability axioms and the separation axioms. And these serve a couple different purposes in topology, but one of the main results which they underlie is the question of when topological spaces are what are called metrizable. And we will talk about one result in this direction called the Urisohn metrizability theorem. Okay. So there's a couple different reasons that we're interested in these types of axioms. So very broadly speaking in mathematics, part of the reason is because topological spaces in general don't really have a lot of structure. That's kind of the point. They're supposed to be viewed as generalizations of the structures that you get in real analysis. But just a topological space by itself, you might not be able to prove very much about because you don't have more structure. So as is often the case in mathematics, the more structure you put on the objects that you're talking about, the more that you expect to be able to prove about them. So these axioms are essentially working in that direction. They're additional criteria that we can put on our topological space such that we should be able to prove more about them. Now, that being said, these are quite motivated. A lot of topological spaces, and in particular, metrizable spaces, which sort of motivate these notions in topology, all satisfy these axioms naturally. So these axioms that we'll talk about definitely don't come out of nowhere, but a lot of interesting topological spaces will already have these. Right. But more specifically, so in the context of topology, these countability and separation axioms are relevant for proving metrizability theorems. So topological spaces in general can be viewed as a generalization of real analysis, right? And then the structure there is a metric space. So a very natural question and one underlying a lot of topology is what constraints do we need to put on our topological space in order to ensure that it has the structure of a metric space? That's what metrizable means, right? So it turns out that there's a couple of metrizability theorems in topology, and all of them have to do with these so-called countability and separation axioms. And certain combinations of these are enough to ensure that one can put a metric on your topological space in the sense that the topology is defined via metric topology. Right? And then from another perspective, a particularly important class of topological spaces are what are called manifolds, be that topological or differentiable manifolds. And a lot of this has to do with the differential structure. So this is one level of structure that you can talk about for these things, but also certain topological requirements are put on these spaces in order for them to be well behaved in a sense. And these topological requirements are particular countability and separation axioms. Right. And then these manifolds are interesting from the perspective, or really broadly throughout mathematics, but certainly from the perspective of geometry. Okay. So we'll start with the countability axioms. So the basic idea here as to why we'd be interested in such axioms is that we don't want too many open sets. We want, this is a very rough statement, but this is saying that we want some control on what's essentially generating the open sets for our space, and we don't want them to be too many, right? So countability referring to countable. So we have two notions of countability here, first and second countable. And second countable will turn out to be a much stronger statement than first countability. Okay, so for the first countability notion, a space is called first countable if every point has a countable basis. So what this means is that associated to any given point of our topological space, there's a countable collection of sets such that any given open set or neighborhood containing the point, there is some index which is sufficiently large that such that every element in that collection with index above that is contained in the neighborhood, right? So this notion looks quite a bit like something related to convergence. This is almost like a epsilon notion of convergence that you'd see in real analysis. And this is exactly the context in which this is relevant in topology as well. So you can talk about a notion of what it means to converge to a point in a topological space. There are some subtleties with this in topology, actually, in terms of the uniqueness of points that it's converging to, but in any case. So in general, for a topological space, what will be true is that if there exists a sequence of points of some set that are in some set that converge to a point X, then X is in the closure of that set. That's always true for a topological space, but the converse is true if the space is first countable. So in particular, that if we have a point in the closure of a set, then we can essentially construct a sequence of points converging to that point in the set. Right? And this is done using that countable basis, right? So you can basically just essentially take neighborhoods of increasing size away from the limit point and just start selecting points in there, and then that will have to converge to the limit point in the topological sense of the word. Right. So that's the first notion of countability. Now, the stronger notion is what's called second countable. So in this case, not only do you have a countable base at a point, but you have a countable basis for the topology. So when we were talking about the rough idea that we don't want to have too many open sets associated to our topology, what we mean is that all of these open sets are generated by this countable basis, right? So recall that a basis is a notion that you talk about for defining topologies. This is like giving a preferred class of sets, which can be used to build up the topology. You have a notion of a basis. You have a notion of what it means for a topology to be generated by a basis. This is saying that that basis has to be countable, right? So this in particular implies first countability. You can use this countable basis pretty easily to construct at any given point the uh, countable collection of sets that are used for the countable base, right? But this actually turns out to be quite a strong assumption in the sense that not even every metric space is necessarily second countable. Right? Okay. So there's a couple things that second countability implies. The two major ones are the Lindelof property. So this means that every open cover of our topological space has a countable subcover. So this is kind of like compactness, but for compactness, it would be finite subcover. This is going to be countable. And second countability also implies that the space is separable. So this means that there should exist a countable dense subset of the space. So dense means that the closure of the set should be equal to the space itself. Right. And then going back to the manifold sort of motivation for talking about second countability, in terms of the countability axioms, second countability is generally what is assumed in the definition of a manifold. Okay, so now we'll start out with a particular separation axiom, I think which ties in particularly nicely to what's discussed in real analysis. So this is a relatively weak separation axiom, which is called Hausdorff. So a topological space is called Hausdorff if for any distinct points, there exist disjoint open sets, neighborhoods, containing these points. So this means that we can separate any two distinct points of our topological space by open sets. In terms of the separation axioms, we're going to go through a couple which are progressively stronger than this, but this is the one which is generally assumed for a manifold as well. Okay, so an implication of the Hausdorff condition is that single point sets are closed in the topology. This is actually also sometimes taken as an even weaker separation axiom itself. But then there's an analog of a result which is familiar from real analysis, and this is saying that compact subsets of Hausdorff spaces are closed. So this statement in real analysis is that compact subsets of metric spaces are closed. So the connection of these two results is that metric spaces you can prove pretty straightforwardly are always Hausdorff. And you do that essentially by taking 2 points. There's going to be some distance in the metric separating them. You can essentially separate them by open sets of balls of smaller radius than the distance between the 2 points, basically. It's pretty easy to construct the disjoint open sets in a metric space. But the upshot is that a metric space is always going to be Hausdorff. Right? So in particular, that implies that if we're trying to prove some kind of a metrizability theorem, uh, the space better at least be Hausdorff, right? Okay. So by contrast to the countability axioms, where we're really trying to limit the number of open sets in a sense that the space has, for something like these separation axioms, we were trying to ensure that there's not too few open sets, right? So Hausdorff is asserting the existence of disjoint open sets separating points, right? So that's saying there should be more. There should be quite a few of these, really, in a sense. But in terms of, I mean, there's a variety of different separation axioms you can talk about of differing strengths. But the three which we'll focus on are the Hausdorff condition, the regular condition, and the normal condition. And if you assume that one point sets are closed, which is implied by the Hausdorff condition, then regular is stronger than Hausdorff, and normal is stronger than regular. So normal is the strongest one, which we'll be talking about. And these all have to do with separating points and open set and closed sets from each other, essentially. So the regular separation axiom says that we can always separate a point and a disjoint closed set from each other via open sets. And the normal condition means that we can separate disjoint closed sets from each other also via open sets. Okay. So assuming one point sets are closed, normal is the strongest of these conditions, regular is second strongest, Hausdorff is weakest, but there are also stronger relationships between these notions. So in particular, if you throw in the fairly strong assumption that your topological space is compact and Hausdorff, then that's enough to say that it's going to be normal. So Hausdorff plus compact is normal. And then in terms of regular, you can show that a regular space with a countable basis is normal. Now, the space having a countable basis, that's just, I mean, the countable basis part is just second countable, right? So this is saying that if we take this separation axiom of regular and we combine it with this countability axiom, this strong one, second countability, that's enough to say that we have a normal space. Okay. So the goal is to prove something like a metrizability theorem. So given this separation axiom and this countability axiom, the space should be metrizable. It should be able to be, the topology should be able to be defined in terms of a metric. So before you prove a theorem like that, you want to know something about its converse, right? So we already said that every metric space is going to be Hausdorff, right? So it better at least be Hausdorff. But actually, it's even more than that. Every metrizable space is normal. And the proof is actually quite similar to showing the Hausdorff case. So we know this now. So whatever assumption the converse is going to have, the resulting space has to at least be normal, right? And then the goal is to prove exactly what this converse is. Right. So one metrizability theorem is called the Urysohn metrizability theorem. And it says that if your topological space is regular and it has a countable basis, this means that it's metrizable, right? So regular with a countable basis was one condition that we gave for the space to be normal. So this is saying that a very specific class of normal spaces is necessarily metrizable. You could do a little bit better than this, trying to get a precise, I guess, like necessary and sufficient condition for metrizability, but this is one of the original results in this direction. So the proof of this is actually quite involved. The idea is that you're supposed to construct an embedding of your regular with countable basis space into a metric space and prove that it's a homeomorphism onto its image. That's enough to prove metrizability. But actually constructing this embedding is quite technical in the sense that you need to construct very specific continuous functions, starting with just the regularity and the countable basis part to get this embedding. And this depends on what's called the Urysohn lemma. And this is actually true for any normal space. So regularity and the countable basis implies normality. So you can use this lemma. And this lemma is actually quite subtle. So I'll maybe leave it at that for the sake of this outline. But I'll be posting some more videos related to topology and this theorem in particular in the near future. Okay, thank you.